This is the second video about my trip to Switzerland. If you have not seen the first, then click somewhere where there is a box maybe, or there will be a link down there to see the first video, which was about just being in Geneva and doing a bit of mucking around in Geneva. This video is about when we went to CERN, because I am a huge massive physics nerd. Ice cream! I'm also a child, but yeah, if you don't know already, I do maths and physics at the University of Warwick, so to call me a physics nerd would be a bit of an understatement. So the Wednesday we got up fairly early because we had our tour at CERN was booked for like 11 or half 10 or something like that, so we had to get up kind of early to get the tram there, and so we did. And the reception at CERN, where we went at CERN, is really cool. There's this thing on the floor that like lights up and everything, and I told you I'm a child. We did actually end up getting there early, so we went to they have like a little kind of museum-y type place called Microcosm, which we went and had a poke around at. Here is me with a plasma ball. Before we actually went touring around the place, we were all gathered for a presentation about what the LHC does and what CERN are trying to achieve and things like this. So if you don't know, CERN sort of originally stood for European Council for Nuclear Research, only it was French, so it's Conseil Européen pour la Recherche Nucléaire, hence CERN rather than ECNR. And you will have probably heard of the LHC, also known as the Large Hadron Collider, which is basically a massive underground ring. It has a circumference of 27 kilometers. That's like the one piece of information that's stuck in my head, where they accelerate things to very high speeds and smash them together to see what happens, essentially. In slightly less simplistic terms, they accelerate protons to very close to the speed of light and then smash them together. That bit was fairly accurate. There's not really another way to say that. The really high energies of the protons means that when they smash together, they can make bigger particles, which then decay almost instantly into lots and lots of really smaller particles, which are then spread out, something like this. T-shirt from CERN. And that's what they detect. So they detect these lots of little particles that all sort of blare out, and use that to try and put together what happens in between the protons smashing together and this happening. And given that I'm only in the first year of my degree, I can't really tell you much else. I'm sure that there are lots of sites online that would be able to give you more detail if you're interested. I'll try and find some and put them down under my bed. I can do that now. So we had this presentation telling us this, which we kind of already knew given that we were all physics students. But once we got that out of the way, we all got on a coach and we went to look at the control room of the AMS detector. And this is the point where I get my internets out to check my facts. So AMS stands for Alpha Magnetic Spectrometer, and this is nothing to do with the LHC. It's a little detector thing that is on the side of the International Space Station. But the research and the data and everything and all of that all goes through CERN. So we got to stand and look at the people in the control room who were looking through all this data as it came in from the ISS, and it was fairly boring really. It was just a room with lots of computers. But they did have a big screen at the back which had like the Earth, and it was monitoring where the ISS was in terms of where it was above. And it was quite interesting to see how much it moved in the time we were there, because it only takes the ISS 90 minutes to do a complete orbit of the Earth, which meant that while we were there it started off above North America, and by the time we left it was somewhere above Africa. And what the AMS does is essentially look for antimatter. So another quick science lesson. Everything that we see is made of matter, because if antimatter and matter come together they annihilate and they both disappear. So obviously there is no antimatter anywhere near us, because if there were, there wouldn't be us either, because we're all made of matter. So what the AMS does is sit on the side of the International Space Station, which is a pretty cool place to sit, and monitor the things that come through it, and to see if they're matter or antimatter. And obviously if it picks up antimatter, that's quite a big thing, because it means that there could be stars out there that are like anti-stars made of antimatter rather than made of the matter that we know most things are made of, or the things that we can detect up to now are made of matter. And the reason we're so interested in whether there is antimatter out there is because when the universe was created in the Big Bang, matter and antimatter will have been created in equal quantities. So the question is, why are we all here, basically? Why did all of that matter and antimatter not annihilate into nothing? Why is there matter here to make us? And obviously if there is some antimatter still left in the universe, that will give us more ideas as to how to answer that question. But the answer to that question is still probably a very long way off, and at least a physics degree away from me. So once we'd finished gawking at the people in the control room of the AMS detector, we got back on the coach and had a short drive to France, where we actually got to see one of the detectors of the LHC. So we're back to the protons smashing into each other and exploding and making pretty patterns like this. So the LHC actually hasn't been running for a couple of months now, which meant that instead of just going to the warehouse, which is built somewhere above where this detector is, because the LHC is quite far underground, about 100 metres underground, because it's not turned on, it meant that we could actually go in and see the detector, which was really cool. So like I said, we went about 100 metres down underground, down, you know, lifts, hard hats, that kind of thing, and there was a door and it was like, now this door is usually kept locked, you know, all the keys are kept, are monitored and blah blah blah. But because it's turned off, we can just open it. It's like, alright. And we went through, and you've probably seen pictures of detectors at the LHC, and they're like this big, and then there's like a man that's like this big at the bottom. And it doesn't quite sink in until you're stood there. And it's like this big. And you're like this big. And it is quite impressive. And the detector that we saw was CMS, which stands for Compact Muon Solenoid, which probably means about as much to you as it does to me. It's one of the detectors that is trying to look for the Higgs boson, and so that found the Higgs boson-like particle a while back. It's not confirmed that it is the Higgs boson, but it is a boson that is similar to the one that they thought they were looking for. It's all very complicated, and no one is quite sure what's certain, so you can't say anything for definite yet. So this is the kind of language that gets used a lot. And that is pretty much it for my incredibly nerdy trip to Geneva. I'll put some links down under there for like Wikipedia pages for the detectors and stuff like that if you're interested. If you're more interested, feel free to ask me questions in the comments and I'll try and do my best to answer them. I can't promise anything given that I'm only a first year undergraduate, but I will try and direct you towards something that might help if I can't answer questions myself. Oh, I sound so stuck up. I'm sorry. But I'm really interested in this kind of thing, and like I say, we do actually know some of this from our course, so I might be able to answer questions. Feel free to try. And so I will see you in my next video. That is all. Goodbye.